Okay, let's look at topic 1.2, reflections and stretches. A reflection of a graph creates a mirror image in a line called the line of reflection. Reflections, like translations, don't change the shape of the graph. However, unlike translations, reflections may change the orientation of the graph. When the output of a function y equals f at x is multiplied by -1, the result is going to be y is equal to the negative of f at x. This is going to be a reflection of the graph in the x-axis. And when the input of a function y equals f at x is multiplied by a non-zero constant b, the result is going to be y is equal to f of b times x. It's going to be a horizontal stretch of the graph about the y-axis by a factor of 1 divided by, or 1 over, the absolute value of b. And if b is less than 0, then the graph is also going to be reflected in the y-axis. Let's have a look at what those mean. In example 1, it asks us to compare the graphs as y equals f at x, y equals the negative of f at x, and y equals f of negative x. Given the graph in A, given the graph of y equals f at x, graph the function y equals negative f at x, and y equals f of negative x. And for B, how are the graphs related to the graph of f at x? Well, in our first one, we'll notice that y equals f at x is in blue, and y equals the negative of f at x is reflected. Every y value becomes the negative of what it was before. So if it was positive, it became negative, such as D. Went from 4 to -4. And if it was positive, if it was negative, like -3, it became a positive 3. So when you look at the graph on the right, on the top, you'll notice that every blue is reflected onto a red. There's two invariant points. Those points are where the points don't change when you have a reflection. One of those points is going to be point C. The other point is going to be at 4, 0. This is a reflection about the x-axis, and every point x, y becomes x and the negative of y. In our second graph, we have y equals f at x and y equals f of negative x. This time, you're going to see that it's going to be a reflection about the y-axis. And there's no stretch on it. X still stays as x, so there's no stretch, but there is a rotation or a flip or a reflection about the y-axis. That's why D becomes D prime, A becomes A prime, etc. So every point here is going to be xy maps onto negative x and positive y. And for part B, it says that the transformed graphs are congruent to the graph of f at x. The points on the graph f at x relate to the points on the graph of y equals negative f at x by a mapping of x, y goes to x, negative y, as we wrote on the last page. Notice that the point C maps onto itself, so C prime 1, 0 and C 1, 0. This point's called an invariant point. And the points on the graph of y equals f at x relate to the points on the graph of y equals f of negative x by the mapping of xy goes to negative xy. That was all said on the previous page, so let's move on. Let's talk about vertical and horizontal stretches for a moment before we do another example. A stretch, unlike a translation or a reflection, changes the shape of the graph. However, like translations, stretches don't change the orientation. When the output of a function y equals f at x is multiplied by a non-zero constant, say some value of a, the result is written as y equals a times f at x. Or if you divided both sides of that equation, you would get y divided by a is equal to f at x. It's a vertical stretch of the graph about the x-axis by a factor of the absolute value of a. However, if a is less than 0, there's also going to be a reflection in the x-axis. Now let's look at the second one. And this time, when the input of a function y equals f of x is multiplied by a non-zero constant, say b, the result is going to be written as y equals f times b of x, where x was the old input, b of x is the new input. It's going to be a horizontal stretch of the graph about the y-axis, this time by a factor of 1 over the absolute value of b. And if b is less than 0, the graph is also reflected in the y-axis. Let's take a look at that in an example. So here we are, given the graph of y equals f of x, transform the graph of f of x to stretch the graph of g of x. And we're going to be showing that in red. Describe the transformation, state the invariant points, and state the domain and range. First of all, if g of x is 2 times f of x, this is what it's going to look like, with the red being the new function g of x, where it's 2 times f of x. Do you see the vertical stretch? Secondly, if b is 1/2 f of x, every point y is times by a half, and that's why the red now is only going to go up half as far. In example 3, we have the graph of y equals f of bx. Given the graph of y equals f of x, transform the graph of f of x to stretch the graph of g of x. Again, that's going to be shown in red. Describe the transformation. So here we go. Notice that in y equals f of x and y equals g of x, f is going to be 2 times x. So if you took every point x and times it by 2, g of x, where it was -4, 4, now it's going to be -2, 4. So the stretch actually shows up as being divided by 2. Every y value is going to be divided by 2. And when it's 1/2 f of x, notice that every y value now is going to be divided by a half, and so therefore it's going to be stick out further. So when we had the point 4, 4, -4, 4, it's going to become -8, 4. In example 4, we're asked to write an equation for the transformed function. So we started out with the blue function and it moved to become g of x, the red function. Well, when you notice, we're first of all going to examine some points. Well, one of the points we could look at, I'm going to draw a dot, is 4, 4. 4, 4 becomes 4, 12 if you move straight up. That means that the original function would be multiplied by 3 to get it up to 12. So we could say every point xy is going to go to x and 3 times y. Or we could say g of x is 3 times f of x, or g of x is 3 times the absolute value of x. That would describe that graph. Now, that's describing it as a vertical stretch. However, we could also describe this by a horizontal stretch. So we're going to say or. We could say xy in the red is going to go from when x is 2, or from, when x is 6 and y is 6 to x is 2, y is 6. So it's going to stretch these third as much. So we would say that every point xy would map onto 1/3 x and y. That is going to be a horizontal stretch of 1/3, whereas in the last one, where it went to x 3y, that was a vertical stretch of 3. So both ways describe the same thing. Let's move on to part B. In this one, the blue simply becomes the red. So there's no stretch, all there is a reflection. So the shape of the graph hasn't changed. There's just going to be a reflection in the x-axis, about the x-axis. And we can say xy goes to x and negative y. That means that f at x goes to negative of f at x, and g of x is equal to the negative of the absolute value of x. So in summary then, the function y equals f at x is our transformation. Y equals the negative of f at x is a reflection in the x-axis. The mapping is going to be written as xy goes to x negative y, and it's shown by the picture on the right. The blue transfers to the red, and there's two invariant points on that graph. For y is equal to f of negative x, that's going to be a reflection in the y-axis. And its mapping is going to be written as xy maps onto negative x and y, and that's where the blue graph now is going to flip and be reflected about the y-axis, and it's going to become the red. In the third one, we have y is equal to a times f at x. That's going to be a vertical stretch. So that means that the vertical stretch about the x-axis by a factor of the absolute value of a, and if a is less than 0, then the graph is also reflected, and every point xy goes to x and a times y. So if a is greater than 1, you'll see that it's going to be shifted up. If y is equal to f of b of x, now it's a horizontal stretch about the y-axis by a factor of 1 over b, the absolute value of b. And if b is less than 0, then there's also going to be a reflection in the y-axis. This mapping is shown as xy maps onto x divided by b and y. So notice it's going to become a shortened graph when b is greater than 1.